So we have an excellent guest speaker today, Professor Jeonghwa. So he is actually going to be here this entire year until December-ish? January? Okay, so he's here at UNH. He's a visiting scientist. His background, he completed his Ph.D. in naval architecture and ocean engineering, something very relevant to most of us here, in 2016 at Seoul National University in Korea. He did a lot of cool experimental fluid mechanics work then, which we're hoping he will get to do some again while he's here. He was a postdoc for 2 years and then joined the Department of Naval Architecture and Ocean Engineering at Chungnam National University, which has since been renamed to the Department of Autonomous Vehicle System Engineering. And his research focuses on the design and analysis of towing tank models in naval tests and analyzing operational data with real fleets. So as you're watching his talk, think about the fact that we have this great well of knowledge who will be here for a year. And again, thank you for giving this talk. We also ambushed him midweek this week and said, would you be willing to give a talk? So
2 days notice.
so we are very, very appreciative, very happy to have him here. So take it away.
Okay. Right. Thank you very much for introducing me. Actually, Tracy is my official host for this visiting year. So I'm very appreciative for Tracy to giving such a chance. And yes, this is 2 days presentation. That means Tuesday afternoon, Tom told me to make some presentation, so I patched up my old works, but it was written in Korean, so for 2 days I have time to translate into English. Some may be broken, but just very just please understand it is 2 days. Okay, so I'm Jeonghwa, and actually my field is naval architecture and ocean engineering, but I am more focused on naval architecture. So it is very classic word. So naval architecture is just kinds of shipbuilding engineering, but it's more designing and production of all kinds of ships. So Korea have some strength on these kinds of things rather than ocean engineering, I think. So in Korea, if someone says I am in naval architecture and ocean engineering, and then most of them works for naval architecture. And my department changes name like this, autonomous vehicle, something like that. But I'm not that kind of person actually. I'm very classic one. And when I joined my university, all the faculty asked about me, what kinds of program do you use? They expected autonomous thing, but I said, oh, I like Microsoft Excel. That's all. Because I am an experimentalist and just want to see everything is under my understanding. That means some kind of black box or programming, even in Fortran or Python, something like that, is not in my taste. So it would be very basic and low technology, I think. Anyway, okay, then let's begin the biography. And how long can I take? 30 minutes or 40 minutes?
40.
40? Oh, okay. Yes, I'll try my best.
What did you want to hear? You want to
if I feel tired, I can cut it. Okay, so all right, and I got my PhD on turbulence experiment for ship hydrodynamics at 2016, and then after that I visited very short time in Lausanne Polytechnic in Switzerland for cavitation experiment, and after that I just worked for postdoc and then moved to current university. And my research interest, and 5 years ago, my first topic was turbulence in multi-phase flow, but it was not financially supported by Korean shipbuilders or Korean government. So this is in fifth place, and first one is ship dynamics modeling. So today's presentation will be about ship dynamics modeling. I hope you guys enjoy this. Anyway, so my first topics in graduate school days was ship model test. Something like this. Also, there's one towing tank in Chase building, like the towing tank facility. I had a similar one. So we like to tow the ship in waves this big. So I was holding the ship, and when the ship is going in state design speed, then ship's released and it is propelled by itself on the target. And then we measure the motion of the ship. Actually, this ship has some fluid in department, assuming some damaging condition. So it has some motions even in following seas, and this is high-speed vessel model test for resistance. I don't remember the speed, but around 7 or 5, 7 or 8 centimeters. And here's the waterjet propelled amphibious vehicle supported by Korea Marine Force. Okay. So after towing tank experiment, I focused on flow visualization test. So all the figures are experimentally acquired of CFD. So stereo PIV measurement of the propeller wake field, and the wave height field was measured by depth camera around one cylinder and regular waves. And this is my PhD thesis. Here's one leather body. And there's one wave pattern and wave breaking. So I measured the flow structure behind, underneath the wave break region by stereo PIV system and made some turbulence structure analysis like that. And after that, when I moved to current university, my present university, there's no towing tank, and so I need to find another place for experiment. It was outdoor condition, so we made some test models. We call pre-running model, so we can radio control or just make some autonomous operation. So this is amphibious vehicle model, and this is one surface combatant model. So we made maneuver test like this and acquiring some data, and I like to make some dynamic system from the result. That's what I'm doing now. So I will introduce about this kind of thing. Yes, actually this model ship costs about 50,000 as far as I remember, but I got 2 times of capsize of the model ship in this place. It's very expensive and very horrible experience in my life, because my supervisor got mad and go to and evacuate the ship. So I cannot do by myself, so I hired one diver to get the model ship back, and I refurbished them, and I did the experiment. Okay, so till next 30 minutes, I will make presentation about principle of ship dynamics in maneuver. Actually, maneuver is somewhat similar to control. So if you are familiar with control theory, then you can find that ship maneuver is in very low level of hydrodynamics or dynamics. And so here's some principles like ship maneuverability and Newton's second law, hydrodynamic modeling. And after that, if we got model, or if we want to get the model, then we need system identification. So conventional one and some contemporary ones are presented here, and data-driven modeling based on PCA or PCR is what I am doing now. So I will introduce this kind of thing. Okay, so most of audience are in mechanical or ocean engineering, so I can introduce what's going on in naval hydrodynamics or naval architecture, how they think. So characteristics are, first thing is extrapolation. So we don't care about the full scale things. We want to know what we cannot know. That means we do model test and we extrapolate to full scale dynamics or full scale hydrodynamics from model test. And we are very conservative, I'm sure that, and I can say that very proudly, because for all kinds of shipbuilding, the design failure cost very high. That means even one collision of ship or one design failure of ship or any kinds of thing cost very highly. So we are very conservative when always worrying about some kinds of new things. And surely high Reynolds number for our cases, but in the field of oceanography or climate things, some things, then our Reynolds number is relatively very low. So yeah. Anyway, for me, it's high enough. And ship neighbor hydrodynamics concerns fluid scaling, focusing on wave-induced problems. So fluid number is basically deals with some gravity-related phenomena. That's why we focusing on fluid scaling. And interestingly, I do model test, but model test resources and facility are very limited. So people like to CFD or any other numerical approach. In these days, even in these days, some people use potential flow theory for wave-induced motion of ships, but it works well. And we are conservative, so we are satisfied. We are satisfied with them. So that's all. That's what is going on in naval hydrodynamics. So there are some major fields of naval hydrodynamics like resistance, propulsion, maneuver, and sea keeping. These days I am working in maneuver, but actually my major was in resistance. Okay, so based on ship resistance, I will introduce how ship hydrodynamicists to think about this problem. So let's say ship suffers resistance, surely. Ship has resistance when it's going through the water, and then there's viscous resistance and wave-making resistance. Viscous resistance is about the boundary layer friction, so it's about Reynolds number scaling. And for wave-making things, it's about gravity. So fluid scaling is required. And if we design model test, then okay, we can make Reynolds number and fluid numbers to be same with the full scale ship. Then it's the basic principle of model test. But the problem is we do experiments for water, so the model speed cannot be same if we based on we suffer Reynolds number scaling or fluid number scaling. So if we want to make same Reynolds number with the ship, then the test model speed should be over Mach 1.5. It doesn't make sense. So we make same fluid number, then it's just 2.1 meter per second. Now we are somewhat happy with them. So we do make experiment based on fluid number scaling. Surely there's some other reasons, but this is the main one. We cannot make Reynolds number similarity in towing tank test. Anyway, so if we got same fluid number, then Reynolds number is around 100 or 200 over 1. So Reynolds number seriously reduced in the first in the model scale. Anyway, so if we for resistance test, model test, we do model test at the same fluid number with the ship, and we measure the total resistance of the ship, model ship, by one load cell. And we made the non-dimensionalization, and we need to divide viscous resistance and wave-making resistance. But how? In 1957, there's one correlation line for Reynolds number and resistance coefficient for viscous resistance. So using this equation, this formula, we can compute this, and the rest of them residually is regarded as wave-making resistance coefficient, and is the function of fluid number. So we can say, oh, this will be same between model and full-scale ship. And then we can recalculate the viscous resistance coefficient of the ship's Reynolds number, and then we can add them to get the resistance of the ship. So basically, we do experiment based on fluid number, but there's difference between Reynolds number, and fortunately, Reynolds number is not so sensitive to Reynolds number variation. So we just use these kinds of empirical formula to treat Reynolds number difference between model and ship. It is very common in naval hydrodynamics. And then there's some towing tank around the world, and the towing tank guys made some components to make some standardization or recommended guidelines for model tests. Because this is very conservative field, so everyone wants to make accurate experiment and accurate analysis on that. So there's no room for innovation, I think. Because I'm young in that field as well. Anyway, so ITTC usually get their own conference for every 3 years, and in US, as far as I remember, University of Iowa and University of Michigan is a member of ITTC because they have some towing tank, just similar with this one. But anyway, they are labor architects, so the League of Labor Architecture runs this kind of thing. Very long introduction, but now I will talk about the ship maneuverability. Basically, ship maneuver is achieved by rudder control. Rudder is usually located end of the ship. We call it stern. So stern propeller and accelerated flow makes flow goes through the rudder to make additional lift force. And you may know about this steering wheel of very old ships. Actually, it works like this. So you turn the wheel and then one lever, we call it tiller. Tiller is moved to make the rudder deflection. It's all same even in modern ships. So there's some hydraulic system to turn the rudder, and then you can turn the ship. But usually ship has 3 degrees of freedom or 4 degrees of freedom motion, but we have only one channel of rudder deflection. So all the motions are coupled. So even for this kinds of large supercarrier, you turn rudder and it suffers yaw motion and sway motion and roll motion all together. This is more detailed explanation of the ship maneuver or dynamics during maneuver. So as I said, rudder, we control rudder to make maneuver of the ship, but rudder usually initiate. At the very first time, we turn rudder and then the ship start to move. But when ship begin to turn or in yaw motion, then the ship hull itself suffers Munk moment to maintain the turning. So usually we say rudder just initiate, but after that, ship motion is dominated by hull itself, not the rudder. So sometimes when ship is turning, we deflect rudder again, but it never responds because ship dynamics is already dominated by hull itself. And for designing of ship, then ship needs to be stable enough to keep the course from external disturbance. That's the main requirements for shipbuilders. We call it course keeping ability. And in addition, ship should be unstable enough to change the course easily by given rudder control. That means if we want, ship needs to change its heading easily. But if we don't want, ship should go straight. That's some conflicting requirements. To deal with them, we need to make a larger rudder. So if rudder is large, then we can satisfy both requirements. But ship owners doesn't like that because it increases high building cost of the ship, and sometimes it makes additional drag or difficulties in stern arrangement. So for naval architects, designing rudder always is kind of conflict and compromising. And the ship maneuverability is, yes, it is important. So IMO, the International Maritime Organization, rules criteria of ship maneuverability. So if you make a ship, I mean not a boat, ship, registered ship, then you need to do maneuverability test after you built the ship and before register the ship. It should pass the maneuverability exam for criteria. There are some tests like turning circle test, just making circular turn, and zigzag test. These two are very important. And if ship have some difficulties in hysteresis in small yaw rate, then we do additional spiral test like this. So making big turn and rudder deflection is getting larger and larger and larger to make some spiral. But ship maneuverability is tested after made the ship, but ship costs very high. So we need to predict at the design stage of the ship, So ship maneuverability must be accurately predicted before sea trial. If the ship is in sea trial and it's proven that the ship does not satisfy these kinds of criteria, then ship owners may refuse the ship to be delivered. Then it's all the loss of the shipbuilders. So shipbuilders like to predict all the maneuverability, even the ship does not exist yet. But full-scale experiment or full-scale CFD is practically impossible. Some may try, but because of high Reynolds number, but we need to know about the viscous friction of the ship, so it's very wide multi-scale problem, so it's not practically impossible in very urgent ship designing process. Sometimes we need 2 or 3 weeks for getting the hydrodynamic performance, but full-scale CFD may not meet the requirements. And extrapolation is common. Extrapolation from model test is common, and prediction of time history of ship is usually needed. So we do maneuver simulation using ship hydrodynamics modeling. That's what we do. To explain maneuver simulation in very briefly, then we know equation of motion, F equals to ma. And if we have hydrodynamic force model, then it's just the estimation of force onto the ship based on current status like speed or rudder angle. Then we can estimate the force, and then by integrating the force and resultant acceleration, we can make time history. We can predict the time history of the ship. So this is ship maneuver simulation for us, and my task is to develop hydrodynamic force model, because I cannot change equation of motion. Alright, and then maneuver simulation is all done in same methodology for researchers. So hydrodynamic force model is my main concern, and it is very it was conventional aspect. So usually naval architects focused on IMO criteria. After that, nobody cares about that. Those very well-trained and very experienced captains steer the ship. So it's all his responsibility. Once the ship passes IMO criteria, then nobody cares about ship's maneuverability. But the world has been changed for autonomous vessels, and autonomous vessel steers by itself usually, and it gets its route and it makes rudder deflection to keep the route. But ship hydrodynamics model should be very accurate and need to reflect all kinds of external disturbances. So even the very well-trained captain or very old captains makes mistakes like this in maneuver. But what happens if we make them to be autonomous thing? We are sure more collision and more accident will occur temporarily. So better hydrodynamics modeling can predict these kinds of accident and making some better maritime world, I think. Okay, long introduction again. I have just 50 more minutes, and I have 30 slides. Okay, I need to hurry. Okay. I'm getting tired. Okay, so the objective of ship maneuverability is just a prediction from model test. That's all. Let's keep it. And you may know that 6 degrees of freedom, but for ship maneuver, we use 3 degrees of freedom motion on the water surface. Surge, sway, yaw has been treated, but recently people like to include roll motion, because roll changes somewhat yaw characteristic of the ship. And then we use 2 coordinate systems. Earth fixed is just Earth fixed, and horizontal body fixed coordinate system is fixed on the water surface. So even the ship have roll motion, the body fixed coordinate never tilt with that. We just keep the body fixed coordinate system to be parallel to water surface like this. So ship roll angle is just kind of state variable, but it is relevant to the coordinate system change. That's the very important thing for ship hydrodynamics on the water surface. And we have an equation of motions. I will skip it. And then, okay, we need this right-hand side term for force and moment, and we need to model it. But there's three kinds of force, proportional to acceleration, and about steady motion, and hydrostatic one. Yes, and then we do hydrodynamic maneuver simulation with the model, but we got model for model scale. We got modeling for scaled model, and we want to extrapolate to full scale, and using simulation, we can get time series of trajectory and motion of the full scale ship to figure out that whether the ship satisfies IMO criteria or not. That's it. And there's some very classical fluid dynamics theory of added mass. Usually, it's very important for us in very conservative way. So I think it's undergraduate course for Rankine over and potential flow, something like that, in steady condition, steady flow. What happens if the Rankine over makes some acceleration? Then the streamline around it changes from yellow to blue. So the streamline by acceleration, the streamline, yellow streamline is pulled by the body in here and pushed by the body. So there's some change of streamlines around the ship, even in inviscid flow. So it causes additional force, linear or proportional to the acceleration of the body. That is called as added mass, and very important in ship dynamics. Anyway, so there's some empirical formula for ships added mass or added inertia. Added second moment of inertia for estimation for ship hydrodynamics. And hydrostatic is also important for ship, but is usually used as a lighting moment. So even ship heels, then the ship stands again by the lighting moment. It is called as lighting moment, and ship's weight and GZ is our characteristic length of the lighting arm. So it is hydrostatic one, and rest of them is the objective of system identification is usually finding steady motion. So force and moment onto the ship is function of linear velocity, angular velocity, and ship's roll angle, heel angle, and propeller revolution rate, and rudder deflection angle. So we need to make the modeling of these inputs and put this output. Some years, some decades ago, there's a whole ship model. So we need to find 5 input variables for 2 output variables. We need to model like that. But in 1980s, Japanese research group suggested, then we can divide the propeller and rudder model. It's physics-based model, so they are just calculated from its dimension or geometry. And then hull form is the only objective of system identification. So we can make a simpler approach for system ID. So in these days, all the shipbuilders or naval architects use this kinds of approach, so-called component model, and more specifically, MMG model has been used. So the problem is how to define or how to structure this model. Usually, Taylor expansion is used for system identification. So we need to find all the coefficients to complete these kinds of model. Then how can we determine all the coefficients? In conventional way, we do captive model test, and some new methods are all suggested by people like me, but it's very conservative field, so it's just on the paper. No industries use new new approaches. They just do captive model test for 40 years. So the captive model test is kind of system identification, but we can force the ship to move in exact designed way. So we can make static drift, or we can make circular motion, or we can make some other motions, and we measure the force onto the ship during the ship's designed motion. So ships in post motion, then we can measure the force onto ship to complete the model. It's a very conventional way, but it requires lots of towing carriage runs. That means 1 or 2 days of experiment, but usually commercial towing tank schedule is very busy. They all arrange the test for resistance, sea keeping maneuver, something like that. So the more experiments, more towing carriage run is not so helpful for them. And another problem of captive model test is that these symbols are captive model test cases, and these clouds point clouds are real ship motion during maneuver test. Then, okay, the captive model test for sway and yaw motion, it makes some sense. But for roll motion, we doesn't try coupled yaw, sway, roll motion for captive model test. That means we need additional some mechanical gadget to perform the model test, but it's expensive, so nobody cares about that. So just based on these these crucial things, then we need to model to predict these kinds of motion. So it may be difficult, or sometimes it's not accurate much. That's the problem of captive model test. So some people suggested then we can run pre-running model test and then get some data for hydrodynamics modeling. But the problem is, if we do pre-running model test, then we cannot measure the force. Force is moving now. But we can get kinematic things like motion or trajectory. So these kinds of force and moment is very important, but it is just some kinds of intermediate variable for the system ID. That's the problem. But anyway, people tried Kalman filter in 45 years ago, and still 10 years ago we do Kalman filter, and recently, very recently, my MS students and I did some optimization of coefficients based on these kinds of approach. But in these days, there's a lot of good optimization library for any kinds of problem. So if I look outside of naval architects, then there's lots of good tools. So we just bring one them without any understanding, and it was just a single layer perceptron, not a multi-layer. It was a single layer perceptron optimization. So I asked this about my friend working in robotics industry, but she was so amazed. It was around before he was old. Anyway, so it was around 40 years or something like that. So still you use this kinds of thing, or still you need this kind of thing, then yes, we are conservative. Anyway, it was quite good, interestingly. Anyway, so we did some optimization, and we found that 19 coefficients for system ID is too much for 8 degree of freedom for input output system. So the ship dynamics model can be simpler if we try to reduce the number of required coefficients for system ID, and then we can design the model test more in concise way. Similar test or similar research was done in Osaka University. So, they do pre-running model test in low speed maneuver in very random way. They call it random maneuver, but actually it was done by manually random way with one radio controller. Anyway, so they insisted that it was good. Yes. So I'm happy to find that okay, others are doing similar things. Yeah, sometimes. Okay, and then still there's one more question. The system ID based on free-running model test uses kinematics, and the force and moment should be the final variable, but in this method, it is just intermediate one. So can we, there's one more question, can we estimate the force and moment acting on the hull during free-running model test? Answer is just yes, it's very positive, because we know acceleration, and if we multiply mass and added mass, and then yes, it should be the force acting on the ship. But it's not so common in my field because it's so conservative way. Okay, so anyway, we tried that. Someone else also tried that, but it was not regularly used for ITTC. Okay, anyway, we can, based on the equation of motion, we know ship acceleration and velocity, something like that, and mass and mass. And then propeller and rudder force should be known. Because, and then we can get the hull force component. So propeller and rudder force can be directly measured during free-running model test by attaching some load cells on the appendages, or estimation by validated CFD analysis, or existing MMG model is also good for estimation, so we can use it like this. And then we can get hull force and hull moment during free-running model test. This is one ongoing project. Basically, it was supported by Office of Naval Research globally for US Navy, but the project was done, and still we are working on the ship for making better improvement of the design. So Robot OS2 is the operation system for this model ship, and we can estimate the global force of the whole ship based on RTK GPS, a initial measurement unit, and rudder and propeller force is measured by some load cells, and we can need some control appendages, onboard data logger, something like that, and safety functions, not for make ship capsize. So this kind of model ship is built in my laboratory, and we bring it to the outdoor condition to make some maneuver test, and we can make the hydrodynamics model of the hull. That's what we are doing. And there's one topic. This is the last topic, and we have 10 slides. We have only 1 minute. Okay, so
You have 5 minutes.
Thank you
5 to
very
10
much.
minutes, yeah.
Okay, 5 minutes is enough. So in these days, I am focusing on principal component analysis. It's very old concept. So but we found that ship dynamics is highly coupled one, and it is non-linear, but it's not discontinued or not so complicated, I think. So with small non-linearity and highly coupled motion, then we can use PCA for understanding what's going on. PCA is kind of gray box approach, I think. Not physical and not fully data driven. So at least we can explain it, and then by explaining, we make sure that it will work outside of the training data. That's very important for ship dynamics. So PCA is in my field, I mean the turbulent fluid dynamics, then PCA has been known as proper orthogonal decomposition. And in Tuesday, Tom told me EOF is also common name for PCA. So it's very old technique, and everyone uses this kinds of technique by their own. The principle is you have some data like this, scattered like that, but you can rearrange the coordinate system or axis to explain this data well in this way. But it's wrong because we can adjust the mean or nominal point to the origin and make these kinds of transformation, and with just one axis, we can explain the data, approximate the data. That is PCA. So ship dynamics is 8 degrees of freedom, I mean 8 variable problem, but they are highly coupled. So we can use smaller number of axes to explain ship dynamics if we do PCA. This is just mathematical thing, so I will skip it. So what we are doing is doing some random maneuver test of shape. And then we got cross correlation and we got eigenvectors. It is, this is 6 degree of freedom motion problem at the initial stage. But anyway, we need four eigenvectors. I mean, the degree of freedom can be reduced into 4 from 6. And then we can explain 90% of the physics with reduced number of eigenvectors. So it's good. And then we expand it into principal component regression. Regression is we have 4 eigenvectors to explain the system, and then usually we have the data of ship motion is 3 variables or sometimes 3 or 4. Then we can estimate the rest of them based on the coupled phenomenon or coupled physics explained by PCA. So back to the PCA, if we know x1, then we can also estimate x2 based on these transformed axes. This is the results of ours. And then the PCR-based hydrodynamics model has very strong points that it can predict or extrapolate out of the training data sets. Once we fully understand the physics, then it suggests good axis for extrapolation. So usually we do 3 tests, zigzag, and turning circle test. Red, black ones are conventional model test for pre-running test. But ship dynamics has been found in more wider regions, the gray one, I mean. So our task is based on this red curve or sometimes in black, adding black one, we need to predict or extrapolate the all gray regions, hydrodynamics of the region. But PCR works well. So we are happy with that. Okay, so we estimate Hall force and moments from free-running model test, and the plain PCR sometimes doesn't work. So we introduce dummy variables. You can find that these are original variables, but we added 2 more variables, just a combination of existing input variables. And then we can find that it can weight more to the initial eigenvectors. So in this case, we have 7 variables, but we know 4 variables. We need to find the 3. Then we can utilize 4 eigenvectors only. But still, there's some important eigenvector, but we cannot utilize for PCR. But adding some dummy variables, then now we know 4 and 2 more variables as on dummy. So there's 6 variables that we know we need to find 3. Then we can utilize 6 eigenvectors for PCR. So here's the rest of them is not so important, then we can fully utilize all the important eigenvectors for system ID. Using that kinds of dummy variable things, then we have compared the original variables and dummy variables. And the dummy variables hydrodynamic model agrees with the original training data set for reproduction, and also it very accurately predicts the trajectory of random maneuver cases. So in my laboratory, we like to call it a MIL-P, called multivariable identification or something like that. So it contains dummy variable and some nominal state description, something like that, for ship hydrodynamics. And also it predicts roll motion quite well. So conclusion is I'm happy with it. That's all. Okay, so this is my end of my presentation, and thank you for listening.
Any questions?
Oh, I have a question. The dummy variables that you called on the PCA,
Yes.
did you just do a you just multiplied, you just did a combination of some of the variables you had? Did you test out different combinations to see which one had a
Yes.
better component?
Right. So till now, to find the best dummy variable is the main task for us, but it's so labor concentrative way. Not me, my students, all trying combinations to find the better one. Till now, these are better, but I think there's some good way to find the best combination of dummy variables, numerically or mathematically, but we are still want to find them. Is that enough?
Yeah, because there are methods where you can, instead of projecting them onto available variables, you just project the space,
Right.
and then you find the variables after the fact.
Yeah.
So you don't really worry about the individual variables, more of a combination of them at the end. If that makes sense. Your axes aren't going to be
Yes.
on your variables.
I cannot visualize them, but anyway, in a very high dimension,
Yeah.
they are all. You're right.
That's cool.
Okay.
Thank you. Yeah, that is.
I think you're the first one who tries it, right?
I was wondering if you had to add or consider another variable, like if you were on a really small scale and you had to consider surface tension or something, would that mean you would need more dummy variables? Or would that sort of replace all of them?
I'm not sure I fully understand your question, but I will do my best to explain. Basically, all the variables are normalized to affect equally for the system. I'm still curious about some variables may affect more to be weighted for the system. Is that enough for answer? Okay, so, yeah.
Have you considered using this for any path planning algorithms on autonomous vehicles at all?
Okay, very good questions. But I joined with naval architect, so there's one good person for SLAM or control and planning something like that. So I don't want to interrupt his field in my department. It's totally political thing. But anyway, it goes like that. And I just focus on modeling itself, and how to use model is just open to everyone. So anyone can do what they want.
Yes, thank you for your presentation. So I'm wondering about nonlinear behavior between the forcing conditions and the response of the vehicles. How much do you worry about that? You mentioned that there was not much nonlinearity. Didn't quite fully understand. I was wondering how much you care about that.
You mean the comparison of captive model test and real motion, or?
That's part of it, yes, absolutely. So, how much does your forcing, which can be very nonlinear, interact with your dynamical response?
Right.
Can you reach states that become unstable for the vessel itself, and does that need to be fed back into the design of the vessel?
It's clear. Excuse me. Regarding the non-linearity of the ship dynamics, actually we have no idea how non-linear it is. We have no exact idea on that. That's why we're still using Taylor expansion on that. But now it has been proven that it works well. It's not academic words, but in industry field, they are happy with that. That's why we have been using this for 40 years or longer than that. So still, we are working for find some non-linearity or some kinds of differencing based on free-running model tests. That's why we do free-running model tests. We can find something never discuss it with this kind of thing. Sure, there's VR, something like that, but it's not physical. It's just suggested as Taylor expansion terms. So there may be high order terms, but people like to ignore that because the test condition based for the high order terms are hard to design for towing tank test. So usually we use only third order or sometimes fourth order terms, and experiments are designed for that. And these kinds of experiment or activities to predict the shape of IMO test. So once it passes IMO test, then nobody cares about the maneuver in very rough or brutal way. That's true in the industry. So yes, that's why we still using that still.
Right, thank you.
Does the, maybe I may not understand the details, but the dummy variables that you included in the end, does that imply that there's a portion of the hydrodynamics that you haven't captured in the original physics-based model that are being captured by those dummy variables? And does it give you a hint as to what is going on that's not captured in the hydrodynamic model?
Yeah, it's very good comment, I think, because we want to find some dummy variable contains very important coupled dynamics that never has been attempted for the Taylor series expansion. So by seeing these eigenvectors and its portion contributions, then we may find some, this variable has a 90% contribution for both eigenvectors, and it may make some physical explanation of the system that we are still want to find what is going on based on that. So this is kinds of some research topic. Yes. So I want to find more about the dummy variables, the physical meaning, and how to find that. Yes. Okay.
Well, thank you, just in time. Thank you, Jeonghwa.